Hello everyone. So in this video, we're going to look at some properties of the definite integral that are going to help us later with computations. So as usual, we don't want to have problems involving lots of complicated things all at the same time. We'd like to be able to break them down into simpler pieces, use what we know about the different pieces, and then at the end put it all together. So let's look at some properties of the integral that are going to help us to do that. So we're going to split into simpler things where possible. So here there are going to be several types of results. So what happens if we swap the limits around? So suppose we can say, we know how to compute the integral from a to b of f of x. How can we compute the integral from b to a? Okay, if we swap the limits, it just swaps the sign of the integral. So the integral from b to a is minus the integral from a to b. And why should this be true? If you go back to the definition of the integral where you had delta x is b minus a over n, if you swap the a and the b around, instead of b minus a, you're going to get a minus b divided by n. Everything is going to be swapped around in sign. So that's why it's true. If we integrate from a to a, we will get 0. Whatever, doesn't matter what our function is, you will always get 0. Why should it be true? You can either go back to the definition, or if you like to think in terms of signed areas, a signed area from a to a, it's not going to have any horizontal component, so the area for sure has to be 0. So here are some simple examples. So we know that the integral from 0 to 1 of x squared is 1/3. We did an example like that before. So the integral from 1 to 0 of x squared is minus the integral from 0 to 1. If we swap the limits, we add a minus sign. So in this case, we are going to get minus 1/3 with no further calculation needed. Okay, and the integral from 0 to 0 of x squared is 0. The integral from a to a of anything is 0, so this is just one special case. So this is what happens if we play around with the limits. Okay, so next up, what about if we have two functions and we want to integrate the sum or linear combination of them or something like that? So, okay, let's start with the simplest case. First, we just want to integrate a constant. So here, think of what would happen. We just get c times b minus a. So why is this true? Suppose that c was positive, just for the sake of thinking about it. So let's say if c was positive and we want to integrate c from a to b. Okay, the graph of a constant just looks like a horizontal line. So if we think about the graph of a constant from a to b, this is going to be a rectangle that has height c, and the base runs from a to b, so it has base b minus a. So the area of the integral is going to be the area of the rectangle, which is c times b minus a. Okay, and this also works with c negative, provided you think about signed areas. Okay, the integral of a sum or a difference is just the integral of the sum or the integral of the difference. Maybe the easiest way to see this is to go back to the definition, but it also makes sense from an area point of view, right? At least if f and g are both positive, then if you think of the graph of f plus g, the graph of f plus g is going to be way larger than, it's going to be, the sum. It's going to be larger than f or g separately, so it's going to have a larger area. The area is going to be the sum of the areas. Okay, and the integral of a constant times f, we can just pull out the multiplicative constant. It's going to be a constant times the integral of f. And this also makes sense if you think about areas or signed areas, right? C f of x looks just like f of x, except it's stretched by c in the vertical direction. So we have an area that's stretched by c in one of the directions. Okay, the area is going to get multiplied by c, which makes sense. Okay, so here are some examples. So since we know that the integral of 0 to 1 of x squared is 1/3, let's try to use that to compute the integral from 0 to 1 of 2 minus 3x squared. Okay, so we are going to start off by splitting it. So we said that here we have two functions. We have 2 and we have 3x squared. We can split the difference. So the integral of a difference is going to be the difference of the integrals. So instead of doing it all at once, we can go back to the integral of 2 minus the integral of 3x squared. And then we have 3x squared. We can pull out this multiplicative constant. So we're going to get the integral of 2 minus 3 times the integral of x squared. And now we have everything we need. So here, the integral of a constant is just constant times b minus a. So we're going to get 2 times 1 minus 0. And then we know already that the integral of x squared is 1/3. So we're going to get minus 3 times 1/3. Okay, so we get 2 minus 1. We get 1 in the end. So we can use smaller integrals we know about different components or simpler functions to put together and understand the integrals of more complicated functions that we build up. Okay, next up is additivity. So suppose we don't need g here, just we have one function f, which is continuous on AB. If we integrate from a to c, and then we integrate from c to b, we get the full integral from a to b. So we can split up the domain this way. So why does this make sense? Imagine if c is some point between a and b. The integral from a to c is the signed area from a to c. Then we have the signed area from c to b. And we're saying that if we take the signed area from a to c and the area from c to b, then in the end, we're going to get the signed area from a to b. And if you think just in terms of usual areas, if everything is positive, this would make sense. It also makes sense with signed areas. Okay, so area is additive. So for instance, suppose we know the integral of a function f from 0 to 5 is 10, and the integral from 0 to 3 is 4. How do we find the integral from 3 to 5? Okay, well, we know the integral from 0 to 3 plus the integral from 3 to 5 has to be equal to the integral from 0 to 5. So we know that 4 plus our unknown is 10, so our unknown integral has to be equal to 6, right? This has to be equal to 6 in order for the integral from 0 to 3 plus 3 to 5 to be equal to the integral from 0 to 5. Okay, so area and integrals are additive in this way. Okay, next up we have comparison properties. So suppose we have two functions that are continuous. What can we say about their relationships? So suppose in the simplest case, we just think about f. If f is non-negative, that means if f is always above the axis, then in that case, the integral represented the area between the function and the axis from a to b. So clearly the area, if the function is always above the axis, the area is going to be non-negative. So if f is non-negative, then the integral is non-negative. Okay, next up, if f is larger than g, then the integral of f is larger than the integral of g, or larger or equal to the integral of g. So this also makes sense, right? If we think in terms of areas, supposing everything is positive just for the sake of thinking about it, if f is bigger than g, then that means the graph of f lies above the graph of g. So the area below f is going to include the area below g. So in other words, the integral of f is going to be bigger than the integral of g. Okay, and next up, suppose we know that f is kind of sandwiched between two numbers, between little m and capital M. So we have this bound on f, we know a constant that it's smaller than, and we know a constant that it's bigger than. Then we get this, this inequality for the integral, this kind of comparison property. So the integral of our function is less than capital M times b minus a and bigger than little m times b minus a. So why should this be true? Well, we can just use the comparison property so that we had in number 2. So if f is less than or equal to m, then we know that the integral of f, excuse me, then we know that the integral of f is less than the integral of capital M. And we can compute the integral of capital M, right? Capital M is a constant. So the integral of capital M is going to be capital M times b minus a. So we get the integral of f is less than capital M times b minus a. And then same going the other way. So if f is bigger than little m, then the integral of f is going to be bigger than the integral of little m. So the integral of f is going to be bigger than little m times b minus a. Okay, or you could think about it on area in terms of areas if you draw the picture. Okay, so as an example, let's try to use part 3 to estimate an integral. So let's use the comparison property to estimate the integral from 0 to 3 of 1 over x plus 4 dx. So later we'll be able to do this explicitly, but not just yet. So let's do a comparison. So what kind of estimate do we have for 1 over x plus 4 in the interval from 0 to 3? So we need to come up with an upper estimate and a lower estimate. So let's say we first think about doing the upper estimate. So we have this fraction 1 over x plus 4, and we want to make it larger. We want to find a constant that's larger than it. So if we want to make 1 over x plus 4 larger, there's not much I can do with the top. But if I want to get rid of the x, if we want to make a fraction larger, we either make the top bigger or the bottom smaller. So we want to make x plus 4 smaller, but we know that x is between 0 and 3. So if x is between 0 and 3, and I want to make x plus 4 smaller, if I want to make it smaller, I could plug in x equals 0. So we would have 1 over 4. And then going the other way, if we want to make 1 over x plus 4 smaller, that means we should make the bottom larger. So we should replace x by 3, which is the largest possible value of x. And in that case, we will get 1 over 7. Okay, so just to summarize, we're trying to come up with constants on either side that bound our function. If we want to make a fraction larger, we make the top larger or the bottom smaller. If we want to make a fraction smaller, we make the top smaller or the bottom larger. So that's our strategy to come up with these. Okay, so if we use the comparison property, we do capital M times b minus a or little m times b minus a. B minus a is 3, so we are going to get either 3 over 4 or 3 over 7. Okay, so we saw several different properties of the integral, and as usual, the strategy is if we can understand the smaller components, then we can understand the integral of the sum or the difference or the linear combination, or we can split the domain of integration and so on as usual. Okay, thanks everyone. See you next time.